Okay, hello everyone. I hope you can hear me. So we're going to continue our discussion of the quantum impurity model, Kondo impurity model, and we'll then hopefully finish that today, and then go on to the the very rich physics of the Kondo lattice model. But as you'll see, there is a close connection between what we learn for single impurity to what happens in the lattice. So the Kondo model is basically shown here. You have a conduction band of electrons that are free to move, and we just treat them as non-interacting. There's an impurity spin at the origin, and the only interaction is between the spin of the conduction electron on this site, should it happen to have an odd number of electrons, and the impurity spin. So we studied various properties of this model by perturbation theory in JK, and I gave you a gentle introduction to the RG type ideas. And the basic physics was that at high temperatures, this spin is basically free to rotate, and this gives you the Curie response. So it's a weak perturbation on the conduction electrons. But as you lower the temperatures, then what happens is that the coupling JK flows to infinity, and assuming it's antiferromagnetic, of course. And in that case, these two, what happens is that a conduction electron gets trapped on the site in the limit of large JK, and they form a singlet. Now, actually, the singlet is not as shown. It's much more spread out, because this is kind of the idea of an RG. You keep rescaling your energy scale. So when you're talking about a single site forming a singlet, it's really the whole, there's a cloud here, a Kondo cloud, which forms a singlet. And everything is determined by a single energy scale, which is called the Kondo temperature. And that Kondo temperature is not just JK, as you might naively imagine, but it's something like TK is of order the density of the bandwidth of the conduction electrons times e to the minus 1 over the density of states at the Fermi level times J. So as JK, so as JK becomes small, the Kondo temperature can become very small. So the Kondo temperature determines the temperature below which the spin is frozen into a singlet, and also, the size of the cloud that's around, that's forming a singlet over here. That cloud has a size of 1 over the Kondo temperature, really the Fermi velocity divided by the Kondo temperature. So it can be quite large. But in the RG procedure, you kind of shrink it down to one side, and then you can solve the problem. All right, any questions on that summary? Okay, so now I introduced last time yet another way of analyzing the problem. And really, historically, this came one of the last actors on the scene after the problem was essentially completely understood. So the only reason I'm bothering with this yet another method to get the same physics is, first of all, it's actually the easiest in the end. And secondly, it generalizes to the lattice. But it makes some approximations, which when you first look at it, seem kind of too simple. How can it be that simple that you just make these simple approximations and you get all this complicated physics? But actually you do. And so there's some lessons to be learned there. So the idea of this new method is to actually think of this spin, which was, had this awful problem when we did computations, that you couldn't use Wick's theorem. So where you say, okay, let me just represent the spins by some new fermions. I'm going to call them F. Pretty soon I'll call them spin-ons, because that's what they become once you go to the lattice, because they are fermions that somehow whose only role is to carry the spin. But they're not free fermions. They have a constraint. The fermions are never allowed to hop from one side to the other. They're just constrained to have the fermion number, the total fermion number of 1. So there's only 2 possible states, either a fermion would spin up or a fermion would spin down. So that's the original states of the spin. So the radical idea is that you could take this fermion representation and just apply Hartree-Fock to it, good old Hartree-Fock. So now you have the Kondo interaction. The Kondo interaction was something like SD dotted into the spin of the conduction electron at the origin, which is C dagger 0 alpha sigma alpha beta C 0 beta. And what we're going to do is just factorize this. And if you want to get all the right factors of 2 and so on, you have to look at the notes. But we're going to just represent this by mean field theory of something like, basically you can, and I'll also drop the indices. Well, yeah, we C dagger alpha, it's 0 always, F alpha average times F dagger beta C 0 beta plus the other one, it will be F dagger beta C beta C dagger 0 alpha F alpha, and then to correct for double counting, you call C dagger 0 alpha F alpha. Okay. And in the notes, we're going to call this object, again, not worrying about factors of 2 and so on in my notes. We're going to call this object, this is just a number, we're going to call it Q, or actually Q bar. Okay. So it's Q bar squared here, because it's just the complex conjugate. And then you have Q times F dagger C and Q bar times Q star times C dagger F. So the only difficulty here is keeping track of all the indices. You have SD is also made up of F dagger F from there, and this is just C dagger C, and you just always pair an F with a C. Okay, and you want to preserve the particle number in your pairing. You're not talking about a superconducting state, so this is really the only thing you can do. Okay, so that's step 1, that you do the mean field factorization. So what you're doing here, this is step 1. And step 2, which is okay, you might feel, okay, that's reasonable. But step 2 is a bit more radical. You're going to say that, well, even this constraint, I'm just going to impose on the average, which means I'm just going to have a Lagrange multiplier, which I call minus plus lambda times sum on alpha F dagger alpha F alpha minus 1. So I'm just going to add such a term and then adjust the value of lambda so that the average value of F dagger for F alpha is 1. Okay, so that seems rather radical because the whole idea of the spin was that you should not allow number fluctuations of this new spin-on or this pseudo fermion. But we are allowing number fluctuations, but we just make sure that the average value is 1.
Sorry.
Yeah.
I have a maybe naive question here about this step from the hard constraint to the average constraint. So
sure.
I remember we done something slightly similar like last semester, and then like if it's written in a path integral and it's like the lambda is kind of integrated over, then this corresponds to the hard constraint or the average constraint.
Yes, yeah. So absolutely right. And in the notes, in fact, the notes that are on the website for this course, so that's what I do. I'm just in the class discussion, I'm trying to avoid discuss using path integrals. That's all. But formally, that's what you would have to do. Take a path integral and think of lambda as time dependent in the path integral and integrate over it. Yeah. Since we are not going to do the fluctuations right now, I'm not doing it. But yes, you're absolutely right. Another thing I thought you were also going to mention is that when you have this hard constraint, you also have a new conservation law, and which is the number of fermions at that site, which is always 1. And every time there's a conservation law, there's a symmetry. In this case, it's a gauge symmetry. And we're going to be talking about that pretty soon once we get to the lattice. But for now, we're going to ignore. Just let's understand the mean field theory. So this idea of, I think, of relaxing the constraint and introducing these spin-ons at the cost of a gauge symmetry, that was a brand new idea in condensed matter physics in the, I would say, the late 80s, early 90s. And it had, had an impact on many, many different things, including the study of spin liquids and Kondo models and so on. And it's something we use a lot more today. And this particular idea didn't exist when people were first studying the Kondo model, but it also turns out to be a very powerful way of understanding the Kondo physics. Okay. All right, so this is what you do. And the other statement I'll make is that what you can make, this procedure becomes exact in the limit where the number of spin components is not 2, but n, and n goes to infinity. So alpha, instead of going from 1 to 2, suppose it went from 1 to n. Then as n goes to infinity, everything I said becomes exact. And then you can compute corrections order by order in 1 over n. And people have done that also. And it all works. For this problem, it all works extremely well. Okay, so this is what you do. And now you're just, once you're done with that, you get this mean field Hamiltonian, which I've just sketched how you derive it. In the old-fashioned Hartree-Fock way. If you want to see how it's derived in the path integral, just read the notes. Okay, so you have this mean field Hamiltonian, and it's coupled with 2 conditions. One is just the definition of Q bar, which I just told you. Here, it's convenient to put a factor of JK in the definition of Q bar, because then Q bar becomes an energy. So this is one equation. And the other equation is the constraint equation that determines lambda bar. All right, so now we have to just solve this. You have to diagonalize this Hamiltonian and solve these 2 equations. That's all we have to do. Now you notice that this Hamiltonian is what is a Hamiltonian we've met before. It's exactly the resonant level model, where what I call the coupling W in the resonant level model, which is the mixing of the local level F alpha with the conduction band, was called W. Now it's just called Q. And whereas W was just some free parameter in the resonant level model, here Q has to be determined self-consistently. So roughly speaking, the Kondo physics is basically a self-consistent resonant level model. That's what the low energy physics turns out to be. And that was the reason I talked about the resonant level model indeed to begin with. Okay, so this is a problem we know how to solve. We just, all we do, we can compute all the Green's functions just by drawing Feynman diagrams. You have, every time you get this, you get a factor, now get a factor of Q, Q, and then this goes from C to F to C to F, basically. And these are the graphs you have to solve. Okay, so this is something you've done in the homework and things like this. Also, when we looked at the resonant level model. So you go ahead and do that. And what you find, as I mentioned last time, that the solution for lambda bar is also simple because of particle symmetry, it's just lambda bar equals 0. And so then you're left with the key equation, which is the equation for Q. And this is what it is, okay? So Q bar is equal to JK times Q bar times what looks like very much like what we met for the Linhardt function with the dielectric constant, the polarizability. And what's the difference from the polarizability? One is that, of course, for the conduction band, it's exactly the same thing. It's epsilon K. But in the polarizability, for the other electron here is not in the conduction band. It's localized, so it has no dependence on K. So this has dependence on K and that doesn't. And this omega is essentially the energy of the resonant level. And what is the density of states of the resonant level? That's AF of omega, and that's of course the Lorentzian. And the width of the Lorentzian is Q squared times the density of states, just like we had for the resonant level model. So basically, this is the equation that you get. Now we know how to evaluate the frequency summation here. We did this for the Linhardt function, and it's just the difference of Fermi functions divided by the difference of energies. But now the whole momentum and integration over energies is very different. Because the only K appears here, this is just an integral over the density of states. And the other thing you just average over the Lorentzian. So we can do that later. So now this is essentially the Linhardt function where only one of the electrons, say, oh, this is really like a particle hole bubble. So you have a particle, which is a mobile electron, and the hole, which is stationary, or vice versa. Now the Linhardt function we found, was completely well behaved at low frequencies. It was, it had just give the density of states. That was the compressibility of a free Fermi gas. But here, because one of the bands is dispersionless and the other is dispersion full, it becomes more complicated. So you have to carefully evaluate this integral here. And I do that here. So this is the integral over the density of states of just where only one of the particle or hole is dispersing, the other one is not. Other one has a fixed energy omega. So first of all, you just replace the density of states by a constant and integrate from minus d to d, as we did last time in the RG treatment. Go to 0 temperature and just replace these by theta functions. And now you just have to bite the bullet and do this integral. And when you do it carefully, you get the log divergence. And that is essentially the Kondo log appearing here. So what you see is the Kondo log is somewhat analogous to, I should have, also drawn this graph here. So you can think of it as a graph like this. This has this is the energy EK, and that has energy omega. It's a particle hole bubble, and in that particle hole bubble, the new difference is that from a previous treatment is that this omega is dispersionless. And because this omega is dispersionless, doesn't depend on momentum, you get this log. So that's really a simple way of understanding what the Kondo log is due to. Yeah, and as we'll see very shortly, when we go to the Kondo lattice, this is no longer true. And in some cases, omega can acquire dispersion. And that's how you can turn off the Kondo effect, because you can turn off the Kondo log. All right, so now once you've got that log, you now have to integrate over the Lorentzian of a width of a certain width, and then solve this equation for Q bar. And you do all of that. Well, okay, what I should have done. So you do this, all the integrals, and what you get at the end is the following equation. I should have actually left another factor of Q bar in there. So there's a Q bar here and a Q bar here. Okay. And also over there, of course. Okay, so now what am I trying to get at? Now this equation, which is Q bar log times Q bar, is something we met before. It's what we met in the BCS theory. There was a log from a very different physical argument, and this is the gap equation. The gap equals log times gap. And then you said from there, well, this means there's always, the gap is non-zero. And so you can cancel out the Q bar on the left and the right-hand side of equation 47, which is what I did when I wrote up the notes. But let me defer that for a minute and just dwell on that a bit. So we are trying to solve this equation. And one of the things you might worry about, is there a solution? Is Q bar equals 0 a possible solution? It's always a solution. You put Q bar equals 0, the left-hand side equals the right-hand side. But is that the only solution? Or can you always find another solution with a non-zero Q bar? So one of the things you might worry is what happens is JK becomes really, really small. If JK becomes really, really small, and this integral here is finite, it's some number, and then you can see if this is just some number, that by making J bar JK really small, I can't possibly have a solution, because the right-hand side becomes really small, the left-hand side is just Q bar. And so there's no other solution. So if this thing was finite, then Q bar equals 0 would be the only solution when JK becomes really small. So essentially the spin becomes free and Q bar is 0. However, because this integral has a log divergence, that's never the case. No matter how small JK is, I can use the log divergence. And yeah, and I should really have put the JK. There was a JK over here, I'll put it down here. So no matter how small JK is, I can make, in this case, the left-hand side is becoming really big when JK becomes very small. But I can, because of this log, which can also go to infinity as gamma Q goes to 0, I can find a solution. So there's always a solution with Q bar not equal to 0, no matter how small the JK. And that's really the physics of the Kondo effect. No matter how small the coupling of the spin to the environment, it will get screened into a Kondo singlet at a very low temperature. And what is that temperature? Well, you just solve this for gamma Q, and it is exactly the Kondo temperature. So this gives you the value of gamma Q, which is the energy scale again. So there it is. That's the basic physics of the Kondo effect. And now I've given you a reasonably honest derivation of the value of the Kondo temperature, or the width of the Kondo resonance at the Fermi level. Okay, so that's the end of the discussion of the Kondo impurity model. And any questions?
But even if we, like now we know we have two solutions, like how do we know which one is correct?
Yeah, okay, so then you have to do more work. You look for which is the lower energy solution. And you always find that the non-zero Q bar solution is the lower one. Yeah, so I haven't done that work, but you're absolutely right. You have to do that check. And that's, you know, if you think about it, that's very usually the case. You know, if you just think about some free energy, here's some free energy as a function of Q, you know, it has an even function. So one possible form of the function, and it has to be, can't go run off to minus infinity as Q goes to infinity. So quite generally, you know, you can say, well, there's two possibilities. It looks something like this. And so this means there's only one solution, but we have proven that's not the case. So what else could it be? Now we know there's a solution at Q equals 0, has to be symmetric. So the only possible shape of this curve is something like this. And this tells you that now indeed two solutions, Q and minus Q are the same thing. And from just by looking at this, you know that this can only happen with three solutions where there's a stationary point of the energy if these two are lower in energy. It's hard to get, you know, if you wanted to get a stationary point up here, you would have to get 5 solutions, something like that, because there'll be another maximum here. So there'll be a solution here, a solution here, and so on. So that's, of course, that could be what's happening. You have to really check it. But this is why, because these curves are usually quite simple, it's always the case if you have a non-zero, not always, it's usually the case when you have a non-zero solution, it'll be lower in energy. And this is the general reason for it.
Thank you.
All right, so now let's go to the Kondo lattice. So we're done with that. Next chapter, we're going to deal with the Kondo lattice. And really, I've set things up, hopefully, in a way that we can do this very quickly. So, well, at least write down the mean field equation extremely simply. So what is the model we're looking at? So now we have a bunch of conduction electrons, which are hopping around on some lattice. Again, I'm only drawing a 1D lattice, but really you should think of this as a 2D or a 3D lattice, C alpha. And then you have a bunch of impurities. no, not impurities, spins. Let me draw a different color here. So you have spins on every side. So these are S, D, I. And the C is also, I have a site index, I. Okay. And there's a coupling between the conduction electron and the mobile electron and the stationary electrons, and that's JK. And there's a coupling on every side. So this is what's called the Kondo lattice model. Okay. There's also another sort of interaction we can put in. And in fact, we will do that shortly, but I'll postpone that for a while, just to keep things simple to begin with. And the other interaction we could possibly include would be another interaction here between the spins directly. And that's also an exchange interaction, and it's usually called the Heisenberg coupling, J sub H. But now we're going to put J sub H equals 0. And when people have both Jacob's K and J sub H, it's sometimes called the Kondo-Heisenberg lattice model. Okay, but right now Heisenberg has been put to 0, and we only have the Kondo interaction. So that's the model we're going to solve. So we just turn the crank with our usual mean field theory now. So now we're going to take our SD on site I. I just put a site index on everything I just did. It'll be F dagger I alpha sigma alpha beta F I beta with a 1/2. And then I have a bunch of constraints for every sum over alpha F dagger I alpha F I alpha, no sum on I equals 1. And that's a very important point. Okay, so this is how we're going to represent the Kondo lattice model. So let me make one point, which will become really crucial as we continue our discussion, probably at the next lecture, which is once you do this, now you're doing, something kind of radical, which certainly was not fully understood when these things started coming on the scene in the late 80s and the early 90s. So what you're doing really, by just using this spin-on representation, you have secretly made this a gauge theory. It's a theory of an emergent, where you're going to, in principle, find particles that carry gauge charges, and there could even be some kind of emergent photon appearing in this model. We'll see that in the first treatment today, I think that there is no photon in the end, which is why this was kind of confusing in the early days. But you really have to allow for it for a proper understanding of what's going on. So why do I say that? Well, what I have here now is an infinite number of conservation laws. On every site, I have a constraint. So I have a model with an infinite, when written in this form, it's got an infinite number of conservation laws. And from Noether's theorem, every time there's a conservation law, there's a symmetry. And what is that symmetry? Well, the symmetry is that you can take your Fi alpha and to multiply by phase factor, which depends on I, and not change anything in the Hamiltonian or any of the equations. So if I look at this this constraint is always F dagger F. In the spin operator, it's F dagger I alpha F I beta. But the point is that this chi doesn't depend on alpha or beta. It only depends on I. And so both the alpha and beta have the same opposite factors because one is a dagger and the other isn't. And the spin operator is invariant under this transformation. And this, you remember from your quantum mechanics, this is precisely what we call a gauge transformation, where you just rotate the phase of the fermion by a space-dependent field. Now, actually, you can even make it space-time dependent to get a full gauge symmetry, but that's more easily done in the path integral language, and let's just leave that aside for now. But that's really a gauge symmetry, but right now it's time independent. But even the time independent gauge symmetries have quite a strong consequence. Okay, so there is a gauge symmetry here, and I might be a bit concerned about it, and I should be. But for now, I say, okay, fine, forget that. Let me just do what worked for the Kondo impurity model and do the mean field factorization. So what will my mean field theory look like? So my H mean field, well, I do exactly what I just did. So I'll have my conduction electrons, which have the usual CK dagger, CK alpha with some energy EK. And then now I'm going to have the Kondo interaction, which I'm going to factorize. So when I factorize it, I'm going to get something like exactly what I had before, but now I just have a sum over I. I'll get a QI on every site. And then I'll have something like minus QI times C dagger I alpha F alpha minus QI star F, I alpha. Of course, that's the key thing. F alpha C dagger I alpha. So I've skipped a step here, but hopefully you see it's exactly what I did for the Kondo model. I write the spins in terms of this F dagger. I put in this exchange interaction. I factorize. I trace over the Pauli matrices and all of that carefully. And what I will get is I'll get exactly the same thing I got for the Kondo impurity model, except this index. All the fermions F carry an index I. So there's an index I here. And also I've also put an index I on the Q, because you're doing the factorization in an I-dependent way. So we're saying that QI is something like the expectation value of F dagger I alpha C I. Okay, so exactly the same dance that we did for the Kondo impurity model, except there are these indices, which are F carries an index, whereas C previously also carried an index. Okay, so that's what you map onto. And we're going to study this, but before we study this, let's just notice one thing. So I had this emergent gauge symmetry here under which F went to like this. But for the conduction electrons, I don't have any gauge symmetry. They're allowed to move around. They have a hopping term, and they're actually invariant under this gauge transformation. So under the gauge transformation, going back to the gauge symmetry, what I do know is that Ci alpha just goes to Ci alpha. So this should also make clear that this is not the electromagnetic gauge symmetry. There's always a physical electromagnetic field that couples to electron number, and under which under that gauge symmetry, C definitely carries a charge. I mean, it's a charged electron. Here, we've just forgotten the electromagnetic gauge field. We just treating the electrons as, only with the Kondo interaction. And the total number of electrons is conserved, the number of electrons being the Ci alpha here. But I'm finding the theory has a gauge symmetry, which is really an emergent gauge symmetry. It's nothing to do with electromagnetism. It's something to do with the structure of the many-body state. And that's kind of a deep new idea that we want to develop now. So there's an emergent gauge symmetry under which Ci alpha goes to Ci alpha. And therefore, this field Q, this expectation value that I've introduced here, Q will also transform. If I do a gauge transformation, my Qi will go to Qi. It will transform like F dagger times e to the minus I chi I. So this Q variable that I introduced, which is just some complex number to begin with, it's not gauge invariant. So depending on what gauge choice I make, I'm going to get different answers for it. So the idea that we now have to start accepting that this Q is itself a dynamical degree of freedom. And it's a boson. It's some kind of collective boson degree of freedom. Somewhat like a plasmon was a new boson that emerged when you did account for the Coulomb interactions. So here, in somewhat analogous way, when you pair in the F dagger C channel, you get this Q boson. And also, we did the theory of superconductivity, when we did the Landau-Ginzburg theory, we started our theory of fermions, and then we ended up with this Couperon, which is the pairing operator of the fermions, which was sort of like a boson, which has some complicated effective action. So we're going to think of Q as some kind of boson. This boson carries a gauge charge, and its expectation value is not equal to 0. So Qi not equal to 0 implies that something I'm going to call the Q boson is condensed. So boson has condensed because it's got a non-zero expectation value of just like the Couperon was condensed in the superconducting state. And this condensed boson has broken the gauge symmetry because it carries a gauge charge. So once you fix the phase of the Q boson, you also have to fix, you've picked a value for chi. That's what people call a broken gauge symmetry. So, or another word that you may have heard about, these are just words that, just I'm throwing out there so that you connect to other ideas we hear. I'm not, right now we don't really need all of this to understand what we're going to learn about the Kondo lattice. So we should really say that Q not equal to 0 implies, what I really should say, Q is a Higgs boson. It's like a Higgs field. And Q not equal to 0 means that you're in the Higgs phase. And this is quite analogous to the theory of weak interactions. In theory of weak interactions, you have the Higgs boson, which then condenses. And because of the condensation of the Higgs boson, there's an SU2 gauge symmetry that's broken. And then there's a mixing between fermions and antifermions, and all the fermions acquire a mass. So in a very analogous way here, you have this Q boson, and when it's non-zero, it mixes the F and the C fermions. And now they don't acquire a mass. What they acquire, as we'll see, is a large Fermi surface. And you get a Fermi liquid state. So that's a long story to just introduce some words that will become more useful later on, which is that the mean field theory that we're now talking about, this mean field Hamiltonian, is really the description of the Higgs phase of a gauge theory. those are, those are useful words, and they're useful because later on that analogy allows you to borrow some concepts and understand things better in what you're studying. But for now, you can just think of this as the same mean field theory we use for the Kondo model. That's all. And never introduce the word Higgs. And in fact, it wasn't introduced in any of the early papers on this subject. It really was something that Senthil, Vojta, and I introduced a bit later and got some mileage out of it, as we'll discuss shortly. Okay, so this is our mean field Hamiltonian. All right, so there it is written out. And now the other point is that since it's not translationally invariant, this is actually even simpler than the resonant level model. You have full translational symmetry. And so you can just go to Fourier space and momentum space. And in momentum space, this is just a two-band model. You've got two bands. You got the conduction band, you got the F band, and then there's some what people call a hybridization between the conduction band and the F band. There's an off-diagonal matrix element. Okay, and so now you can just take this model and diagonalize it and get the band structure. But it's a simple enough model. It's a 2x2 matrix because you've got two bands. So just a two-band model for electrons. And the only thing different from the usual two-band model is that the parameters of the two-band model are determined self-consistently. There's now the Lagrange multiplier lambda bar that has to be determined so that the average density of the F electrons is 1/2. And Q bar, which is the hybridization, has to be determined the same way, just like we did for the Kondo problem. And one other peculiar feature, which actually will turn out to be important, is that the dispersion, the K dependence, is entirely in the conduction band. The F band conserves momentum, but it's dispersionless. It's lambda bar. And this will turn out to be an important feature of this Kondo lattice model, but it really is an artifact of the approximation. In the real world, when you do this very carefully and include other higher order corrections, it's not true that the F band is totally dispersionless, but it's a good starting point. Okay, so now this is it. Here's a Hamiltonian. Here's our Hartree-Fock equations. Solve them for Q bar and lambda bar. That's all. The rest of this lecture will be a discussion of what happens when you do that. But that's the problem we're solving. And again, and now you see the analogy to BCS theory is very similar. There you had a delta parameter, which multiplied C dagger, C dagger. Here the Q bar parameters multiplied C dagger F. And there was a self-consistency gap equation. And here's our gap equation, or the analog of the gap equation, the Q bar instead of delta is equal to the expectation value of C dagger F rather than expectation value of C dagger, which you had for the BCS theory. Okay. All right, so let's, rather than going through the equations, let me draw a few pictures to see how, what the solution of these equations will look like. But any questions on where the equations came from? Now it's just a mathematical problem of solving equations 2, 3, and 4 for Q bar and lambda bar. That's all I'm going to talk about in the remaining 15 minutes. Okay, so everyone get the equation. So let's go ahead and let's at least do something graphically. Okay, but before I do that, let me take my Hamiltonian and write it out in matrix form. I can write it this way: C dagger K alpha, F K alpha. It's a 2x2 matrix. C K alpha. And there's an EK here, which is dispersion full. There's a lambda bar here, and there's a Q, which is off diagonal. That's basically our Hamiltonian. And certainly you know what the eigenvalues of such a Hamiltonian are. EK will be 2 of them, we'll call them capital EK, will be the average of the diagonal matrix elements plus or minus square root of the difference of the diagonal matrix element divided by 2 mod squared plus mod q squared. Okay. You can also do this using Green's functions if you want, which is the way it's done in the notes, and compute from this. So now you have to compute for this Hamiltonian, what is Q bar. So Q bar will be expectation value of C dagger F. So you have to figure out, which states are occupied, and you have to do the unitary rotation. You have to know the eigenvectors of this matrix and work this out. That's one way to do it, or you can do it using Green's functions, which is what's done in the notes. If you do it the old-fashioned way by actually diagonalize the matrix and figure out the eigenvectors and eigenvalues, that's always safer, bit of a mess. But after a while, you get comfortable using the Green's functions and do it a bit quicker. But before I go through that, let me just draw a few pictures. So what's happening here? So we'll draw some band structure. So you've got, I'm only going to draw one section of it. Okay. So here's some energies. And this is K. So this is some kind of Brillouin zone. This is K. Let's say going from minus pi to pi if you were in 1D. And you've got the F level, and you've got the K level, EK. Okay. So let's see. Make sure I draw this properly. All right. So here's the dispersion of. Let me first draw the dispersion. Yeah, let's see. So imagine that EK looks something like this. Just keep it very simple. This is EK. And the F level is that it's constant, lambda bar. So it'll be just some lambda bar wherever it is. This is lambda bar. So that's the C electrons and that's the F electrons. And this is for Q bar equal to 0. You'll see in a minute why I need to, well, okay. So now I'm going to, one of the important questions I have to ask is where is the Fermi level? Okay, so Q bar equals 0, where is the Fermi level? Well, let's say the Fermi level is over here. So the Fermi level is here. And so less than half of the C electrons are filled. So these states are filled and those states are empty for the C electrons. Now, what about the F electrons? Well, the F electrons, they're not coupled to anything when Q bar is 0. So I just want to start from that solution where the F electrons are not coupled to anything. So the number of F electrons has to be 1 per site, because that was our constraint back here. So per spin with an n spin component, for any spin up electrons, the average number of spin up electrons has to be 1/2. Now, how do you get 1/2 as the average number? Well, just let's imagine the temperature was slightly non-zero, just to reduce the degeneracy a little bit. Then if the temperature is slightly non-zero, if you plot the Fermi function as a function of energy, just plot f of E. That looks something like this. So it's equal to 1 here, and it's 0 out here. Where is it equal to 1/2? Exactly at 0 energy. Take the Fermi function and evaluate it. E equals 0, you get 1/2. So that means that really the F level has to be exactly at the Fermi energy when Q bar is 0. And that's in fact what happened in the Kondo impurity model. Even when Q bar was non-zero, it broadened out, but was centered at the Fermi level because lambda bar had to be 0. So here also lambda bar to begin with has to be right at the Fermi energy. So now I should erase this. And so that I get exactly lambda bar at the Fermi energy. So this is the F level, which is right there. That's where my chemical potential is. Okay. All right, so that's the situation you begin with when Q bar, if you wanted to solve the equations and assume Q bar was equal to 0, you want to solve at least the lambda equation properly, you would have to put the F level at the Fermi level. Okay. And now let's turn on Q bar. So these bands are going to mix, and this equation tells us how they mix, but let's do it in pictures. You know how what happens when bands cross and they mix. So I guess let me draw another picture. So take time to draw a picture, take another page here. Okay, so now I have same picture with mixing. Okay, so now let's see if I do this well. So then I have a mixing, and let me do that. So they'll get one band, which is the EK minus, the lower band. What would that look like? Well, if you draw, I can't fit both pictures in the same screen, but anyway, so let me try to do my best to do something like this. And the other band, let me use a different color. Okay, something like that. Okay. So now, so what's happened? So they're mixed over here. And so when they mix, there's level repulsion. And so one band does this and the other band does that. So if you look very far away, when Q bar goes to 0, they would actually cross, but they actually don't cross. It's an avoided crossing. And this energy scale at which they avoid cross, we assume Q bar is small. So this energy scale is basically Q bar. Okay. And now we have to, so say you found some Q bar, these bands mixed, and now you have to fix the Fermi level, fix lambda bar. And how are we going to fix lambda bar? Well, we have to fix lambda bar so that there are two kind of constraints that you have to solve, and now the notes go through that, exactly how you solve it. But one of the constraints is that the total number of electrons should be 1 plus the initial number of conduction electrons. So let's say that the, what do I call it in the notes? Rho sub C. Okay. So here, how many electrons do I have? I have rho sub C electrons per unit cell, of course, per site. And rho sub C, because I'm talking about both spins, is assumed to be less than 1. Okay, so rho sub C is less than 1. And the number of s electrons is exactly 1. So the total number of electrons is slightly less than 2. 1 plus rho C, which is less than 2. So total number of electrons is 1 plus rho C, which is less than 2. So now I have to fill the lowest energy states. That's what free electron theory tells me. I have some band structure, fill the lowest energy states, and find out where the Fermi surface is. So in this 1D picture, the purple band is always below the red band, simply because of the minus sign here, and this square root is positive. So first I have to ask, can I get away with just filling the purple band? Well, how many electrons can I put in the purple band? Well, the number of electrons put in the purple band, like any band with spin, is 2. And the total number of electrons here is less than 2. So in fact, I can get away with filling just the purple band. So the total number of electrons has to be less than 2. So where is my Fermi level? So my Fermi level, which I'll draw with the brown line, is okay. This whole thing should be exaggerated. I should have drawn a better picture. is somewhere over here. So this is our Fermi level. This is KF. And in this region now, notice the fact that this is so small doesn't mean there's fewer electrons. To count the number of electrons, you count K. You just count up how many momentum states you have. And the number of momentum states has grown. So previously, the number of momentum states was up to here. This was our KF for the conduction band. And this is now moved by pi, in fact, to over there. And because now I have 1 plus rho c over 2 electrons per spin per site. So this is my Fermi level, and that point, in fact, includes both the F and the C electrons. So I have what's called a large Fermi surface. And another thing you notice is that at the Fermi level, the band is practically flat, because this band was flat to begin with over here. So the band here is also, it's not exactly flat now because of the mixing, but it's really quite flat, provided the mixing is not so strong. And a really flat, almost flat bands means that your effective mass is huge. Okay, so this is in fact the theory of heavy fermions. This is how you get a heavy fermion in a material like iridium, beryllium-13 or platinum-3. You have a heavy fermion. And it's a heavy fermion because you started with a flat band, you mixed it up, and you ended up putting your Fermi level in a regime which is very, oops, I should have done that. So it's very far away from the reason there was any mixing. So the only place you have a lot of dispersion in the F band is right here. The only place you have any dispersion. But when you get out here, okay, it's very slight. You have to compute it, how slight is the dispersion. And from that fact that it's almost flat, it means that, the energy near the Fermi level, how it goes, Ek is Vf times K, or dE dk, the derivative of the energy with respect to velocity is the Fermi velocity. And the Fermi velocity is written as Kf over m star. So since the velocity is so small, it means the particle is very heavy. And in fact, in many materials, this m star can be 1,000 times the mass of a bare electron. And it's all related to this kind of Kondo physics. All right, I think I'll stop there. And so the text has a lot of equations and manipulations, which go through what I've just shown you here pictorially. Okay, any questions? All right, so today is Monday, so we're going to have a discussion at 9 a.m. on Tuesday. So I think you started having a better attendance and some good discussions, so please try to come because, we are talking about now fairly subtle things, but not so complicated, I hope you agree, once you mastered the art of Hartree-Fock theory. Okay, thanks a lot, and see you tomorrow or Wednesday.